Yes, ma'am.
This is your first 12th chemistry class, right? Yeah, 7 participants.
7 students are on it.
Yeah.
Yeah. So screen is shared, right? Students, are you able to hear me? Those who are online?
Yes, sir.
Very
Yes,
good.
sir.
Okay. Okay. If possible, right? From next class, try to attend offline. Okay, because you'll have better interaction here. Avoid attending only if it is a very emergency situation. Okay. So other than that, everything is clear, right? You guys are able to hear and all those things, right? So ma'am will take over. And she is going to start with the first chapter of your 12th standard, that is solid state. Is it clear? Okay. So those who are here and those who are online, please make sure that the class is more interactive. Like however you maintain the physics class and math class, maintain the same with respect to chemistry as well, so that you can understand the subject better. Is it clear? So ma'am is very much open to answer your doubts. You have any kind of a doubt, please open and ask. Open your mouth and speak. Is it clear? Yeah.
This is your first 12th chemistry class, right? How's your feeling? Yeah, come in. Okay, so far you have completed around 20 chapters in 11th, right? Probably 15 to 20, moreover. Okay. So here today I'm going to take solid state. Okay. So in solid state, before getting into solid state, you have already learnt about states of matter, right? So this chapter connects with that chapter. If you know the basics of the states of matter, it's easy for you to knock this chapter. Clear? So what are all the things you studied in states of matter? Can you be a little bit louder, please? Gaseous state, yeah. Actually, states of matter in the sense solid, liquid, gas. In 11th standard, you have like predominantly you have studied about the gaseous state, and in 12th you are going to study solid state, right? So why? What is the purpose to study states of matter? First, that's my question. What do you infer is like secondary? Why you are studying, and what is the purpose of studying states of matter? To understand conditions. What conditions? Different temperatures, different. Okay. So initially, when I'm asking states of matter, everyone will say solid, liquid, gas. That's an easy one to say. Okay. But the thing is, actually, there is water. Okay. So there is a drinking water. The drinking water, it contains crores and crores of molecules of water. It is not one molecule. Clear? I think you will study about that one molecule, one atom in your chemical bonding. But in physical chemistry, in states of matter, you will not deal with one molecule or two molecules. Lakhs and crores, even it's not crores, it's like infinite, uncountable. It's like you can't count it, right? So this solid, liquid, and gas. Okay, definitely you can see in and around there are many solids, liquid, and gases are around it. There is some force, okay, some force that will decide the matter to attain which of its physical form. Clear? Can you get my point? Okay. So first thing is I'm taking a liquid. Okay. So what happens in liquid? The particles will be how the particles will be. It will not be tightly packed. Okay. The students in online, can you able to follow me?
Yes, ma'am.
Yes, ma'am.
What happens in solid, the particles are all tightly packed, one after another, one after another, one after another. In liquid, what happens? Quite loosely, okay? But in gas, what happens? It will freely move, right? Okay, now I'm taking a liquid, okay? Now I'm just keeping in a refrigerator, in freezer. What happens? It will become ice, right? So what makes that liquid to convert into a solid form ice? Huh? Decrease in temperature. But behind it, there is some sort of forces, right? Forces, right? Okay, there is some force which what happens if the imagine in my hand there is a liquid. So what happens once I'm keeping this in a refrigerator, there is some sort of force. What happens? It binds, it connects the molecule, it connects the particle. It can be of molecule or particle or atom or ion or anything. It connects all the particle, and all the particles are coming close together, and there it forms a solid. Clear? Likewise, I'm keeping the liquid in a gas stove. Okay, what happens? After some time, it will start to boil, right? After boiling, what happens? The liquid will convert it into vapor, right? So there is a force that is acting. That is nothing but your intermolecular force, which you have already studied in your states of matter. Do you remember? Yes, not only intermolecular force. Another one more factor is also important. Okay, coming to my first slide. The purpose of studying states of matter is actually what is the force that is behind this solid, liquid, gas, which makes all the three things are interconvertible. Solid to liquid, liquid to gas. So what force is acting behind it? So you'll be studying about the Van der Waals force, London force, dispersion force, dipole-dipole force, dipole-induced dipole, hydrogen bonding. This is attractive as well as repulsive, Boyle's law, Charles' law, all the things you have studied or not. Studied, right? See, everything in physical chemistry, everything you can apply with the day-to-day life. Boyle's law speaks about the pressure. In the sea level, the pressure will be high, whereas in atmosphere, the pressure will be low, right? And Charles' law speaks about the volume and temperature. Okay, why the pressure is high inside the seawater? Why the pressure is low when you're just going in the heights? Temperatures? But I need a defined answer. Volume is directly proportional to temperature. Okay, so density is equal to mass by volume. You're bringing, but actually Boyle's law speaks about the pressure and temperature. You are saying about Charles' law. No. I'm saying this Boyle's law only connects this pressure concept. This is pressure versus volume. Charles' law is volume versus temperature, right? Boyle's law is the only thing which connects the pressure here, right? So what happens? Very simple. You know, when you're just going down the water, the density of the gas molecules, what happens? The gas molecules will be there. But how the gas molecules will be there? It will be quite far away from each other. Due to the gravitational pull down the water, all the gas molecules will come closer. So the density will be high. Density is directly proportional to pressure. Density is high, pressure is also high. Clear? Can you be able to get my point? It's a very easy and interesting chapter, states of matter. Okay. And when you are going high in sky, what happens there? In sky, there is less gravitational force. So the molecules will be like here, there. So what happens? The density is very, very less. The pressure is also less. Right? Application oriented just study. Okay. That thing only connects the Boyle's law. Clear? Yes. So this you're going to study. This already you have studied in your states of matter. I don't want to get into states of matter because it's a huge subject. It's like an ocean. Now we can get into solid state. Okay. So actually, the Earth is composed by water. Like composition of Earth, it's 70% of water. But in a practical life, in reality, we humans are surrounded by maximum most of the things is in solid state. Okay, liquid and gases will be less in numbers, but maximum and most of the states, just see in this room definitely gas will be there. Okay, but beyond gas, you can see maximum most of the solid things. Laptop, tab, phone, chair, your book, everything is solid. Okay, so in reality, in practical world, when we humans deal with it, we are dealing maximum with the most of the solid materials. Okay, that's why it's very, very important to study about the solid state. Okay, say for example, if this mobile is a solid, okay, definitely it has some properties. Okay, you're going to deal with the properties. Okay, and what are all the types of solids? Crystalline and amorphous. And what are all the types of crystalline solids? Ionic, covalent. Ionic solid is nothing but your sodium chloride, which we are eating, right? Without salt, nothing is like tastier. Sodium chloride. So likewise, each and everything, metallic solids, iron. This building is made up of iron, right? It's a metal. So each and everything practically you are connected with the day-to-day. So that's why you're going to study about solid state. So just get to my first slide. Simple basic 3 forms of matter. Now, go through this question. Students present in online for any matter to determine its physical state, 2 important factors are important. What are they? See, matter everywhere, the matter is present. Okay, breaking of matter. You know this thing, breaking of matter. You keep on breaking matter. At one point, the smallest indivisible thing is known as atom. Okay, you know this thing. So this matter, what decides this matter should to be solid, liquid, or gas? Temperature, pressure. That comes under secondary thing. Primary, intermolecular forces.
Intermolecular force.
Very good. First one is intermolecular force. Second one, very important thing, thermal energy.
Intermolecular space.
Yeah, you're right. Very good. Thermal energy. Okay. So intermolecular force is nothing but the force of attraction or repulsion between 2 molecules, right? Because here we are going to deal with only molecules, lakhs and lakhs of molecules, crores and crores of molecules, right? So that is in my next slide. Intermolecular force. Okay. So next one is thermal force. Yes. As I already said, intermolecular force is nothing but the force of attraction. Okay. Now, my another question, thermal force is nothing but the measure of kinetic energy. How fast the molecules are moving inside the solid, liquid, and gas. Okay. Now, keep your mind free. For solid, how the intermolecular forces should be and how the thermal force should be. Very less, exactly, absolutely right. Because this is a solid. Okay, see, everyone is thinking this is a solid in the sense you are just seeing it is as a cone. But what happens in this, the particles are very closely packed, right? Once it is closely packed, you think the particles can move freely, it can move from one place to another place. No, what about its kinetic energy? It's very, very less. Once it is getting heated, what happens? Nothing will happen, right? So if any external force comes, there the case is different. Okay, the kinetic energy is nothing but how the particle is just moving, how the electrons is just moving. In solid, it's tightly packed, so there is no movement. How it is tightly packed? Because of the intermolecular force of attraction between one molecule and the other molecule. In liquid, both will be intermediate, moderate. Okay, so moderate in the sense it will not have that much of intermolecular force and it will not be having that much of thermal energy. In gases, ulta of solids, intermolecular force is very, very less. If here there is one gas molecule, there will be another gas molecule. So there will be intermolecular force of attraction will be there. You can't say there is no intermolecular. It will be very, very weak. But thermal energy, the gas molecules know it will flow from one place to another place easily. Say for example, imagine you're having a deodorant bottle. In deodorant bottle, the gas is compressed. Okay, so compressed, and inside that what happens? All the gas molecules will be there. Once when you just once you're spraying, what happens? It escapes. But once it escapes, you can feel the aroma all through the room. So what happens? This gas particles move very much faster. So the kinetic energy is more. Intermolecular forces less. Clear? So that is the thing that decides. These are the two major important factors. Okay, the intermolecular force is more and the thermal energy is less, it is solid. Okay, both of the things is intermediate, it is liquid, right? In gas, intermolecular force is very, very less and thermal energy is very, very more. Clear? Clear, guys? Students present
Yes,
in
ma'am.
online. Yes. Now, this is the question I have already asked you. So just write down the point, okay? Do you want me to say, I mean, like write notes like intermolecular forces high, all these kinds of things? You will like make your own notes, right? Yeah. Next slide. What are the general characteristics of solid? It's quite interesting, okay? Have you taken notes for all the things? Students, just like we can go slow with the solid state. Okay, with the solid state, it's easy for you to study the solutions. Okay, little bit things will be there in solutions also. Yes. Now, characteristics of solid. Actually, you can think you have read all the things in the basic level in 8th standard, 7th standard you have read. Okay, but you know each point okay, we can explain for more than 100 lines. Now, how first fixed shape and volume. Okay, so say for example, if I'm taking two solid, if I'm taking this phone, okay, if I'm taking the phone, so in this phone, what happens is this is a solid, its shape is fixed, its volume is fixed. I am placing another solid on the top. Okay, so because of this solid, does this solid change its shape or volume? No. So solid, if you're just taking a big empty box and you're placing a small box into it, definitely what happens, both the boxes doesn't change its shape and volume at any conditions. Okay, now take a sponge. Okay, sponge is a solid or liquid or gas? Solid. I'm compressing it. What happens? It changes its shape. You're saying sponge is a solid, but it changes its shape. What happens there? Huh? Okay, fine. It has air molecules. Yes, it has an air molecules. There is a small holes is present in it, right? When you are applying external force, the sponge, what happens? It will get compressed. Okay, but once when you're releasing the external force, again it will come back to its original position. Okay, that is the power of solids. Yes, sponge is a solid, but what happens there? Again, it can come back to its original shape. Okay, that's what the point is says about the least compressibility. Okay, so if you're just taking sponge, what happened? Many people will think they'll be having a doubt whether sponge is a solid or not. It is a solid, but solid has the power to gain back its original form. Clear? Yes. Coming to the second point, particles of solid have strong force. It has an intermolecular force of attraction. Okay. So what happens here? Because of that only, it's tightly packed. So that only it's called a solid. Okay. And third one is rigid or hard. See, the above point explains a similar thing. Rigid or hard in the sense because of the packing of the molecules, it is strong and it is hard. Fourth one, particles present in the solid can't move from one place to another place. Clear? It can only vibrate and oscillate. Okay, imagine so hypothetically when you are in a crowded bus. Okay, so the bus is like flooded with people. So if I'm standing here, okay, so in front of me there is one person, in right of me there is another person, behind me one person, and in left of me there is another person. Okay, so it's heavily crowded. Okay, so what happens when the bus is moving in motion? What happens? I'll be moving like this, but I don't change my place. I'll be standing here. Okay, but my bodies will be getting vibrated like this. It will be like vibrated immediately when the driver is putting a brake. What happened? I'll go front and I'll lean on the person who's standing in front of me, and again I'll come back to my original position. That is what the thing happens in solid. Okay, so what happens? It can vibrate and oscillate at their position. Okay, it can't freely move. Even if, just take this phone. If it is, if you're just putting it in a vibration mode, what happens? It will vibrate only in this place. It can't come to you and say, the call is coming for you. Come, please attend. It can't say like that, right? So what happens at their position? It can vibrate and oscillate, right? Yes. Do not have fluidity. Of course, solid, it can flow from one place to another place. Water, it is a liquid, yes, it can flow. But solid, it do not have fluidity. Solids have least diffusion tendency. What is diffusion, first of all? What is diffusion? Exactly, from higher concentration to lower concentration. Okay, just imagine it's a similar example. Just take a deodorant bottle. So the gas present inside the deodorant bottle will be having the higher concentration. Okay, once when you just spray it will spread all through the room, and what happens? Its concentration will be getting decreased. It will be having lower concentration. So that kind of thing is not possible in solids. So that's why it will be having the least diffusion tendency. Clear? Yes. Least compressibility, as I already said, sponge and rubber is an example. Gas can be highly compressed. And finally, solids have compressibility of 10 to the power 6 times than gas. See, solids are already compressed, right? Okay. So what happens? Gas can be compressed. Okay, and you can just put it in any form of container. Solids is already compressed. Then only what happens? The particles are all tightly packed. So just they are comparing solid and gas compressibility. Okay, so if you're just taking the gas and solid will be having 10 to the power 6 times more compressibility because the particles are all tightly assembled. That's it. Clear? You understand these characteristics? Okay. Yes. Basics. Okay. Coming to the next one. Classification of solids. Crystalline solids and amorphous solids. Okay. Have you heard about this crystalline and amorphous anywhere? Where? So, crystalline, amorphous means powdery. Crystalline means like it will be having crystals like that you have studied. Okay. See, coming to the first point, crystalline solids, actually, most of the solids are present only in crystalline form. Okay. So particles are all arranged in a regular 3D form. 3D form in the sense, see, imagine in your home, our flooring, when your flooring is made up of tiles. One tile is brown color and one tile is white color. Wait, I'll write some. See, if there is a tiles, if this is in white color, this is in brown color. Okay, so what happens? How it will be laid? Brown, white, brown, so likewise it is arranged. Okay, so what happens? If you're just seeing all through your tiles, it will be having a pattern of white, brown, white, brown, white, brown, white, brown. Okay, so what happens? You're just viewing in terms of one dimension. Okay, if you're just seeing in all 4 dimensions, this is like, imagine this is a cube. Okay, so this is a cube. In all 4 dimensions, what happens? It will be having a proper crystal lattice structure. Clear? Okay, so this crystalline solids will be having a proper 3D arrangement. 3D arrangement means you can view it from all the sides. Clear? So I think you know to draw this cubical form of 3D. It could be like this. This is a general, regular, basic 3D structure of a cube. Okay, so this is actually it is viewed in three-dimensional structure. All the crystalline solids, if you just take salt, NaCl, just take a pinch of salt. Okay, if you just view, if you are just putting the salt in the microscope, when you're just viewing it, what happens? It will show this kind of structure. Even a pinch of salt has this kind of structure. Clear? So this is a crystal lattice. So that is the crystalline solids. Their arrangement will be in the regular 3D structure. But in case of amorphous solid, what happens? It will be not like that. There will be irregular 3D arrangement. Irregular in the sense, take this example. So what happens here? There is one cube is present here. Another cube will be like this. And one lattice point from will be connected on the top. And one point will be connected from the side. There will be no proper arrangement of cubical forms will be seen in amorphous solids. Clear? And second point, what is long range order and what is short range order? I have already said the tiles, okay? Okay, in your home, the tiles will be laid not only in one room, all through your house will be there. Likewise, it will be having a long range order. See, I have said so what happens if you're just taking a very little bit pinch of sodium chloride salt, you can find the crystal lattice. If you're just taking a bulk quantity, what happens? You will find a long range order. Clear? So what happens in case of amorphous solid, you can't find. Okay. So what happens there? There will be a cube. And what happens? There will be an uneven distribution of some lattice points. Again, there will be a cube. There will be an uneven distribution of some lattice points. So what happens? There will be not a regular pattern will be followed in amorphous solids. And the arrangements also will not be proper and unique. Clear? Yes. When you cut it with a sharp knife, smooth surfaces of time. See here, taking okay. So here you can see, you can view two cubes. If I'm just cutting in this direction, what happens? You can easily separate one cube. Clear? And what happens after cutting, you can view the surface will be very, very smooth. In case of amorphous solid, what happens? See, in amorphous solid, say for example, in mid, there will be a lattice point like this. So once you're just cutting it, what happens? There will be, the structure will be of this kind. Right? So what happened? Just look at this point. When you cut it with a sharp knife, irregular rough surfaces of time. So what happens there? The arrangement is not proper. So there the irregular surface will be seen. Here the arrangement is regular three-dimensional arrangement. So what happens here? It will be you can easily cut it and the surface will also be very, very smooth. Clear? Yes. Sharp melting point. What is sharp melting point? See, hypothetically, if I'm taking sodium chloride, will be melting at 100 degrees Celsius. Hypothetically, okay. So what happened? Even at 99.2 or 3, it won't get melt. Exactly at 100 degrees Celsius only it will be getting melted. It will be very sharp and very defined. In case of amorphous solid, if you're just taking plastics, plus or minus 5 or 6 degrees Celsius will be okay. Okay, even at before attaining, if like say for example, if 106 is the melting point, even at 103 degree or 104 degrees Celsius itself, it can easily melt. Okay, so plus or minus 5 degrees Celsius difference will be there in amorphous solid. Yes, coming to the next thing is take it. Next one is anisotropic and isotropic. Have you ever heard this word? Anisotropic and isotropic. Wherever? No. Okay. See, anisotropic and actually this crystalline solids will be having the anisotropic nature. If you're just taking the properties, okay, physical properties, say for example, refractive index or diffraction or electrical resistivity or electrical conductivity, all these properties will be different kind of size or shape or curvature in different directions. Okay, just leave it. Just take this example. I'm taking a diamond. Okay, I'm keeping a diamond here and directly I'm placing a marker. Okay, what is this? This is a pen. I'm directly placing it. Means when I'm viewing it via the diamond, this marker will be seen little bit bigger because of the light is getting diffracted in this way. What happens? This marker will be looking little bit bigger. Again, when I'm taking this marker and viewing it in downwards, it will be quite thin. It will be quite thin. Okay, so what happens here? This property, this diffraction is different in different directions, right? But in case of amorphous solid, take a polythene paper, transparent polythene paper. In different directions, the objects will be looking similar size. Clear? Getting my point? Getting my point? Okay. Anisotropic in the sense there will be n number of properties. All the properties will be differ according to the size or shape or curvature, whatever, at different directions. Isotropic in the sense they won't change. Their properties will not be getting changed. Clear? Finally, true solid they have a definite and characteristic heat of fusion. Heat of fusion is nothing but the conversion of solid into liquid. So this heat of fusion is the amount of heat that you are just giving to that compound or to that molecule to convert it into solid and liquid. Okay, so this crystalline solids will be having defined, like sharp melting point, it will be having a defined characteristic heat of fusion. If NaCl is having this much heat of fusion in the sense, definitely at particular point can be attaining the solid to liquid. Clear? So this amorphous solid will not have that kind of defined heat of fusion. And true solids is nothing but they're all actually real solids. Example, sodium chloride, potassium chloride, silver bromide, silver chloride, and all salts are crystalline solids. All metals are crystalline solids, right? Amorphous solid means you can take talcum powder, plastics, rubber, chalk piece powder, chalk, everything comes under this amorphous solids. Clear with this tabular column? Okay? Yes. Answer this question. Just only see the question. Sorry? Be a little bit louder. Your everyone is saying all the properties that you are studying in crystalline solids, right? See, actually, here I have disclosed it's a pseudo solid, which means it's an amorphous solid, right? Why glass is known as this pseudo solid or supercool liquid? Okay. Have you seen visited what is this place? Okay, leave it. 200 or 300 years old building. Okay, in the 200 what is the palace called? No. Okay, just leave it. So what happens? 200 or 300-year-old building. If you just see the windows, what happens? That window, no. At the bottom of the window, it will be too thick. At the top of the window, it will be too thin.
Just 2 minutes, please.
Yeah. So if you're just looking at the windows, what happened? Bottom of the windows will be too thick, but at the top, what happened? It will be too thin. Okay. What happens there? Already I have disclosed it's a 200 or 300 years old building. In the sense, what happens? This particles present in the glass, due to the gravitational pull, it comes down. That means it comes to the downward direction. That's why what happens at the bottom it will be too thick and at the top it will be too thin. Okay, but you're saying glass is a solid. Okay, solid has a fixed shape, fixed volume. The particles will not move. But what happens here? The particles, what happens? It is though it is taking 200 years or 300 years to move, but still it's moving, right? Okay, that's why this glass is known as pseudo solid or amorphous solid. Super cool liquid in the sense what happens? This liquid is traveling for 100 years, right? So that's why you just Google the image. Okay, you can see the window at the down, at the bottom, what happened? It will be too thick, it will be too strong. Means like the density will be of this much. But at the top, it will be too thin. One way it will be like you know, the thickness will be very, very less. Okay, that is because of the gravitation. Slowly for years it is getting traveled and it will come and settle down at the bottom. Clear? So that's why this glass is known as pseudo solid. Clear with this? Huh? Sorry? Sorry, that's you are saying wall. Huh. See, the materials made of glass is different from the materials that you are constructing the building, right? Right. But this wall doesn't get changed according to size or shape. This wall will not getting altered. Okay, because the compounds mixed in it is different. But glass is made up of, right? So initially, if you're just taking the glass, it will be solid. But what happened? It's not an instant process. It will take years and hundreds of years. Okay, if something happens to this building, immediately it will be getting break, right? But in case of solid, in case of this gas, the particles are slowly getting moved. Okay, it depends upon the compositions. That's why this class is known as pseudo solids. Clear? Yes. Guys present in online, you can understand this thing.
Yes, ma'am.
Okay. Type of crystalline solids. You know, like all salts are crystalline solids. All metals are crystalline solids. Even the non-metals are also crystalline solids. Carbon, sulfur, phosphorus, diamond, graphite, they're all crystalline solids. All powdery substances are also crystalline solids. Okay, so in that they are classified into ionic, covalent, metallic, and molecular. Right. First one is ionic solid. The best example is sodium chloride, NaCl. Okay. Why it is said as ionic solid? Ions. What is ions? It consists of cations and anions. Right. So what happens? The cations and anions will be there. There will be electrostatic force of attraction is between them. Clear? That I have disclosed. There will be an electrostatic force of attraction that will be working between the cation and anion. That is one positive charge, cation is positive charge, anion is negative charge. So what happens? Both of the things comes close together. You know about the NaCl structure, crystal lattice structure. The cation will be small in size. The anion will be large in size. Why the cation will be small in size? Because it loses its electron. The anion will gain the electron. So that, yes, it will be small. This one will be large. Likewise, what happens in crystal lattice, they will arrange cation, anion, cation, anion, cation, anion. Likewise, it will be arranged. So one cation is surrounded by 6 anions. Okay, how? Top, bottom, left, right, front, back. 3D structure. Okay, so one cation is surrounded by 6 anion. 6 anion is surrounded by 1 anion is surrounded by 6 cations. Okay, similarly, top, bottom, left, right, front, back. Likewise, what happened? The arrangement will be there in crystal lattice. And you know, they're all hard and brittle means they can be easily break because they're all soft metals. Sodium, potassium, they're all soft metals. Okay, and note this point. 4th point. They are insulators in solid state. Insulators means they are poor conductors of electricity. As they are converted into aqueous states, they become conductors. What this point? There will be 3 ions, right? So in solid state, what happens? The arrangement will be of NaCl. So what happens in solid state? What happens? It will be there will be no positive or negative charge representation will be there. So simply NaCl, NaCl, NaCl. This Na will be holding the Cl, and this Cl will be holding the Na. But when it is converted into modular, what happens? Right? So this will be converted to Cl minus all. So there is clear. How much free ions are present in a molecule, that much the conductivity. If there is less free electrons, it will be like if there is more free ions, it will be a very good conductivity. Okay, how much free electrons are here? And this NaCl and KCl, they are all ionic solids. Sodium chloride, potassium chloride, silver chloride, silver bromide, magnesium oxide, zinc sulfate, not disclosed. And why they are all ionic solids? Because of the type of free ions. Okay, it is the Cl minus. It is the Cl minus. Answer this question. Sorry? First one decreases, increases. Second one, high or low? High, very good, it's high. See, the temperature is getting increased. How the conductivity will be getting increased? If there are all the particles will be present, right? Once everything gets transported, what starts to move. So what happens if it starts to move? Point, melting and boiling point of ionic solid, they're all tightly packed. Okay. So what happens there? You need to give more amount of melting and boiling point to break it. Okay, to break the lattice, to break the crystal lattice. So it will be high, and here it will be getting increased. Clear with this ionic solid. See what we are seeing is just the basics. Okay. Covalent solids. So actually, this covalent solids is made up of Maximum it will be by non-metallic atoms. Okay, like carbon, sulfur, phosphorus, diamond, graphite, quartz are all the example of covalent. Covalent means already, it's mutual sharing, right? So there will be no kind of cation or anion or present. Only the atoms will share. Clear? So the constituent particles will be atom, and this will be still more strong because they are sharing. Okay, it will be strong and it will be hard and brittle because when they are very strongly bonded, it will be very much hard. And brittle means what happens? Though it is hard, still it is easy to break. Yes. So if, the best example is, wait, I'll come to that thing later. Light dissolves light. You have studied in our organic. Like solvent dissolves like solvent. Ionic solid, most of the solids are salt. Okay, they are all polar in nature. They will dissolve in water, which is polar. Likewise, this covalent solids are non-polar. Okay, polar in the sense it should be having the positive and negative charge. This is charge separation, polarity or dipole, whatever it might be, charge separation. This is non-polar. Okay, there will be no charge separation present here. So what happens? It will be dissolved in the solvents like non-polar solvents, benzene, carbon disulfide. So in all these kinds of non-polar solvents, only this covalent solids will be getting dissolved. That's why I have said like dissolves like. Clear? And again here also the melting and boiling point will be high. Read this point. Sometimes covalent solid decomposes even before reaching the boiling point. What this point? Sorry? Doesn't have charge. Okay. Oil. Water is nothing but just take oil. Oil is an example of covalent solid. Okay. How? Oil is covalent in nature. Do you know that thing? Yes or no? Because there is no free hydrogen bond is present in it. Oil is covalent in nature. Okay. So when you're just keeping the oil in front of the flame, what happens? Have you seen the oil getting boiled? No. Before boiling itself, what happens? The fumes will start to come. Before boiling point itself, it will be getting decomposed. It will be become black in color. That explains this point. Clear? Sometimes, at rare cases like oil, what happens? Before reaching the melting point, it is decomposed like oil. Clear? Sorry? Why is that? Actually, this covalent, if you're just taking any covalent solids like diamond or graphite, it will be having the maximum melting point and boiling point. In case of oil, what happens? See, take water. Water is having hydrogen and oxygen connectivity. Hydrogen and oxygen is nothing but highly electronegativity atom is connected to it. So what happens at one point, this oxygen will releases the hydrogen. In case of oil, no such kinds of thing is present. This hydrogen will not release at any point in case of oil. So that's why what happens before reaching the boiling point, it will be getting decomposed because of the absence of the hydrogen. I think you have studied it in your 6th or 7th standard. Oil is a covalent. No, that's the reason, right? They'll be comparing this water and oil. In water, water is nothing but hydrogen and oxygen are bonded. What is hydrogen bonding? Yeah, highly electronegative atoms. Oxygen, fluorine, nitrogen should be attached with the hydrogen atom. What happens? There the hydrogen bonding is possible. Okay, but in oil, no such kinds of things is possible. That's why what happens? It is getting decomposed before reaching its boiling point. Clear? Now, covalent solids are all bad conductors of electricity. Okay. Now, take notes. Okay. I'm saying graphite is also a covalent solid. But in graphite, there is a free electron. Can you understand? Can you get my point? See, or maximum 90% or 95%, most of the covalent solids are bad conductors of electricity. Best example is diamond. Right? Do you know the structure of diamond? One carbon is attached with 4 other carbon atoms. sp3 hybridization will be there. Right? So I'm taking diamond. This will be the structure. This is nothing but carbon. Okay. So one carbon atom is attached with 4 other carbon atoms. It will be having sp3 hybridization. There will be no free electrons is present in it. If there is no free electrons, what happens? There will be no conductivity. So if there is no conductivity, it will be a bad conductor of electricity. But in case of graphite, what happens? It will be the structure of graphite is like this. Right. So here what happens, this carbon is having sp2 hybridization. Okay, it is bonded with 3 carbon atoms. One free electron is there. You know about the electronic configuration, all such kinds of things, right? Without knowing, you can't understand this thing. There will be one free electron. And one free electron will be moving from here and there. Okay, so this is a layered structure. Okay, so because of that only, this graphite is said as a good conductor of electricity, and this is an exceptional case that is following in covalent solid. Maximum 90% all are bad conductors. Exceptional cases, this graphite. Actually, you know, graphite acts as a very good lubricant in industries. How? Layers. So actually, what is the mechanism followed there is, see, diamond is it's the most hardest substance in the world. Okay, you can cut any kind of, even the big giant rocks is getting cutted by the diamond. But in graphite, what happened in industries, we will be using a big machines which will be having of 1000 degrees Celsius or 500 degrees Celsius. So what happens for lubrication? They'll put oil or grease. Okay, but if it is 100 degrees Celsius or like 900 degrees Celsius, what happens? This oil or grease will be getting decomposed. So for that purpose only, this graphite, they'll replace it with the graphite and it will be acting. See, it will be acting as a very good lubricant. This is one layer structure and this is another layer structure. This is a free electrons. Likewise, it will be getting lubricated. Okay. And next one is metallic bonding. Okay. Tin and metal iron. Okay. So how the arrangement of atoms is present in it? Close. Okay. Because being a metal, they are closely arranged. You are saying it that way. Okay. Have you heard about the kernel? Kernel. Kernel. Where? See, have you seen? Have you done with the electronic configuration? 1s2, 2s2, 2p6, 3s2, 4s2. Out of which 4s2. Electrons. The electron, okay, what happens? First it is still 4s. The lower energy is filled first and then the higher energy. Right? And what happens? This the energy gap between the 4s and 3s. They are known as inner shell. Those electrons who those are already their shells are full. If there is a free electron, this will be represented in this way, right? You can see this picture. This plus is kernel. Okay, so this plus is kernel in the sense it can be of not only iron, it can be of, if you're just taking sodium, valence electron is 1, right? Rest of the 10 electrons will be present inside it. That is, the 10 electrons will be the nucleus and inertial electrons, and the 1 valence electron will be represented in this way. So likewise, in iron, what happens? This will be, there will be a kernel, and all the 8 electrons will be surrounded here. Okay, kernel and all will be surrounded here. Kernel and all the 8 electrons will be surrounded here. So likewise, if you're just taking an iron rod, what happens? There will be crores and crores of iron atoms will be present here. In that crores and crores of iron atom, what happens? There will be the sea of electrons will be present inside. Clear? And what happens? This nucleus, what happens to this electron? And this electron will also have an attraction towards this nucleus, right? So this is known as metallic bonding. Okay. So what happens? Likewise, there will be n number of iron atoms will be there. Okay. The electrons present in this kernel will have an attraction to this kernel also. Okay. Likewise, each electron is bonded. Not only one kernel, with 2 kernel also it will be getting bonded. So that is known as metallic bonding. Clear? So in this case, only all the metals are getting bonded. If you just in S block, you can see the sodium metal, which is like highly explosive, right? So in that sodium metal also, why? Okay, my question. Very, very, very simple, sensible question. Sodium metal, okay, it is highly reactive. But sodium chloride, it is not reacting. You are just you're using in your day-to-day life. How? Sodium, when it is present as a metal, what happens? It has a free electron in it. So when the free electron is present in it, that's why it's showing that kind of explosive nature. Okay, but when it is present in a compound, sodium chloride, it becomes stable. Clear? When it is present as a sodium metal, is unstable. The one free electron is what happening? It is getting revolved around the shell. But when it is present as a sodium chloride, this one free electron will be shared to the chlorine, right? It will not share, it will completely transfer to the chlorine, right? So it will become stable. So that's why that's the difference. As a metal, it is unstable. As a compound, it is stable. That's how what happens here. All the electrons are metallic bonding will be getting formed. Okay. So here are some of the important points. Now, don't worry, every your thing after completion, you can ask the questions. Metallic bond. So here, yes, of course, intermolecular forces of attraction, metals are highly electropositive. Highly electropositive means they can easily donate the electron, they will easily loses the electron. Okay, you can understand the metallic bonding, you understand the kernel you understand, and get to the question. First question. Iron, correct. Because of the presence of valence electron. Iron has 8 valence electron. So what happens? It will be showing more conductivity. It will be a good conductor of electricity. See, this conductivity is based on the presence of valence electrons, right? Coming to second, sorry. Okay. Coming to the second question, before getting to the second question, I think previous slide I have said the ionic in ionic solids the temperature increases, the conductivity increases. Here, what happens? If the temperature increases in metallic solids, the conductivity increases. But still, if you're increasing the temperature, what happens to the conductivity? How? Bond will break. What happens to the conductivity? Bond will break means this metallic bond will break. Okay, covalent bond. Decomposes. No, decomposition will not come here. Conductivity is nothing but the flow of electrons. Right? When any external force or heat is applied to it, the electrons will be moving fast. That is the temperature, right? If you're just giving the temperature, the conductivity, I mean the flow of electrons will be good. If you're giving too much temperature, the conductivity will be getting decreased. The answer is decreased. Why? I'm saying the answer is decreased, and I'm asking the question why. Because they are see, initially when you're just giving the temperature, what happens? The electrons will take the heat, temperature, energy, whatever. It will take the temperature, and what happens? It will start to move. Right? Once you're giving more and more amount of temperature, what happens? Even the kernel will also take the energy. Okay, and what happens? It will start to vibrate. Clear? Can you understand my point? So what happened initially? What happened? When you are giving temperature, the electrons will take it, and electrons will flow in this direction. The current will flow in opposite direction. This thing you right? The electron will go in one direction. The current will move in opposite direction. Once what happens? When more and more amount of temperature is given to a metal, after these electrons are like fastly moving, what happens? This kernel will also takes up the temperature, and it will starts to vibrate very much fastly. So likewise, each and every will face a repulsion. Okay, and after the repulsion, this entire structure will be getting distorted. It will be getting collapsed, and the conductivity decreases. Clear? Metallic question. Okay, change it to metallic solids. Okay. Yes. Can you get my point? The normal temperature, the conductivity increases. If you're raising the temperature, what happens? The conductivity decreases because of the vibration of the kernel. What happens? The two kernels will come close each other and it will face a kind of repulsion. And what happens? The entire structure will be getting distorted and will be getting collapsed and the conductivity will be getting decreased. Clear? That's why what happened if you're just heating iron more and more and more, can easily getting flexible, right? So that is nothing but the structure is getting collapsed. Clear? Finish. Shall we move to the next slide? Another 10 more slides will be only like this. But once we are jumping into the primitive cells, BCC and FCC, it will be quite interesting. Okay, I assure you. Properties of hot, but not all the metals are hot. You just take mercury, it is liquid, right? And sodium and potassium, they are very soft metal. Okay. And malleable and ductile, they can be malleable means they can be thin sheets and wires, they can be produced. Good conductors, of course, because of the free electrons. Luster, of course, all the metals having the lusters, shining nature, color. Free electrons, the free electrons present in the ground state, once it is heated, what happens? It will absorb the energy and it will move to the excited state. And what happens there? It will releases the extra energy and again it will back to the de-excited state. And there the visible range of colors will be seen because of the presence of the free electrons. Because metals, definitely free electrons will be there. And magnetic properties is also because of the free electrons that you will be solving in your DNA block, right? Of course, high melting and boiling point and density will be there, right? Molecular solids. See, molecular solids, right? Look at the stabler column. This chlorine, bromine, carbon dioxide, water is a liquid. Topic molecular solids. But here it is, these are gas. These are gas. This is a liquid. But I have written the topic molecular solids. So what is study states of matter? Okay, first question. These are all gas. Okay, example of molecular solids. How? In lab, you know, in laboratory, they'll take a liquid carbon dioxide. How? Pressure. Okay. Temperature. You have to reduce the temperature. Okay. The temperature you have to take into -degree Celsius. You know, there is states of matter. There is not only solid, liquid, gas. There is plasma and both condensate is also there. But like up to an NCERT level, we are only discussing solid, liquid, gas. What is plasma? Huh? Yes, it's fourth state of matter. I'm asking what is plasma? Super high temperature. It is possible only in sun and stars. Okay. What is Bohr's condensate? Super low temperature. Minus 270 degrees Celsius, minus 280 degrees Celsius. Theoretically, it is not possible. Reality, it's not possible. Theoretically, it is possible. This plasma, actually, the astronauts are saying 99% of the universe, okay, the matter is only present in the form of plasma. Only 1% is solid, liquid, and gas. This is a prediction of astronauts. Right? We are not dealing it with plasma as well as Bohr's condensate because they are having super high temperature. We can't go into the sun and we can't make any reactions. It's not practically possible. But in Bohr's condensate, we can't, reduce it to minus 200. Even we people can't bear minus 2 degrees Celsius or minus 1 degree Celsius, right? And how it's possible for minus 273 degrees Celsius? Here, what happens? They will reduce the temperature in laboratory under certain conditions and they will solidify it. Okay, sodium and chlorine, both the elements combine, both atoms combine together, and then only you are getting the sodium chloride, right? Where the chlorine comes from? Can you get my point? Okay, out of the solidification. Okay, they will reduce the temperature and they will solidify. Okay, then they will obtain. Right? Then only your salt and everything will be obtained, right? But naturally it is there. But in laboratory, what happens? We will reduce the temperatures, right? See, what is London force or dispersion force? States of matter. Right? This London force and dispersion force. Without that thing, you can't move. It is a intermolecular force of attraction will be there, right? When this intermolecular force of attraction is there, your non-polar molecule will be temporarily converted into a polar molecule. Wait, I'll explain. So I think very easy way. I'll try to explain it. See, this is considered this as a non-polar molecule. Okay, yes, yeah. Okay. So what happens? You have to achieve polarity for this molecule A by giving some external force. Okay. So if I'm giving temperature, okay. So if I'm giving not temperature, if I'm giving electricity, that will be easy. If I'm giving electricity, what happens? The flow of electrons will come here, and what happens? See, this is symmetrical. Here the negative charge, here the positive charge will be there, and here the negative charge will be here in the shell, right? So what happens when you are applying high electricity? It is nothing but the electrons will be there. This is also negative and this is also negative in the sense this molecule A will be getting distorted. How it will be distorted? All the negative charge will be going behind the positive charge and it will be getting distorted like this. Do you remember this thing? Yes. Now, again, if I'm taking molecule B, this molecule B, it is also, see, this is non-polar. Okay, non-polar will be symmetrical. That is, the positive charge will be accurately present in the center and the negative charge will be evenly distributed, symmetrically distributed. Okay, and after attaining polarity, what happens? Look at here, all the negative charge is moving behind the positive charge and the positive charge is present here. If I'm taking similarly molecule B, in molecule B also what happens? If an electric field is getting passed, okay, what happens? That molecule B also will be converted into this kind. Right? And there will be a force of attraction between this A and B. This is temporary. This is known as London force or dispersion force. Actually, this kind of force will be seen in your noble gases, helium, neon, argon, krypton, like this. Okay. Now you got what is London force or dispersion force. Okay, so maximum it will be taking place in non-polar molecules, and temporarily they will convert it into polar. See, this is temporary. After that, what happened? Again, it will be coming into a non-polar thing. Right? See, this intermolecular forces, they will be saying this intermolecular forces will be happening in molecules, but maximum it will be taking in gases, especially in noble gases, because the gases are all freely present. Okay, so here also likewise what happened, if you're taking one linear matter, of course there will be some kind of attraction will be there, it will come closer, and again what happened, it will be getting break. That is the stability, stable, unstable, stable, unstable. In environment, for a minute, it will be having that kind of stability. And after 2 or 3 minutes, what happened? It will become unstable. So this will be getting apart, that will be getting apart. This is London force or dispersion force. Clear? Clear? Now clear? Yes. Now say about this dipole. Since you can take this example itself, right? These four are molecules, right? So the kind of attraction between these two polar molecules speaks about the dipole-dipole interaction. That's why I have mentioned there as polar solids. London or dispersion means non-polar solids. Clear? So that are all the examples. Chlorine, and insulators. Insulators in the sense they are all the poor conductors of electricity. Okay, so they have low melting point. Already you are just like solidifying it at a less temperature, right? So you are keeping the temperature of -°C, so they will be having low melting point. Similarly for polar solid, actually this molecule solid, that's why first one is non-polar, second one is polar. Hydrogen bonded solid. Okay. Water, insulator, that will take up electricity, but we are taking electricity from the water. Huh? Can you get my point? We are all taking electricity from water, but I have mentioned here water as an insulator. Why? Exactly, you're right. Pure water is an insulator, right? But the water which conduct electricity will have some salts in it, right? It will have some salts. It will have some electrolytes, right? Salts means definitely there will be a free ions present in it, correct? So pure water is always an insulator, but the water which contains the salts or electrolytes, there it will be acting as a conductor. Clear? So these three are the examples of this molecular solids. Clear? Yes. So we can wind up this class here. Okay. So from next class, I'll start crystal. There is one more thing to discuss. From next class, I'll start crystal lattice and unit cells. And there is one more still a little bit to discuss. I feel that this is the first class. I don't want to bore you with that much level. Okay. So any doubt in this till now? Any doubt? Sorry? Your question stability is like questions are it is there as a questions. Okay, I'll discuss more. Okay, see this solid state is very important. Okay, PCC, FCC, ECC, and you'll see study about Bravais lattices, and you'll see about the efficient number. Efficient number is not important according to your core level, but it is very, very important according to JEE and me point of view. Okay, so there you will be solving some problems. And I think tomorrow is the class. No, there is 1.5 hours is there. So tomorrow you will solve some problems, and I'll bring still more questions. Okay, thank you. See, just go through home and in your textbook, what are all the things I have said in the PPT that is there in the textbook. Read once. Okay, so you'll get a clear picture according to it. Okay, thank you.
Thank you, ma'am. Bye, ma'am.
Thank
Try
you,
to
ma'am.
come-
Thank you, ma'am.
Thank you, ma'am.
Try to come to physical class. Okay, so it will be quite more interactive. Tomorrow I'll ask some questions also, and I'll bring some MCQs. Okay.